Hello everyone, welcome to this next video on classical mechanics. In this video we shall see application of Lagrange equation and particularly we'll see simple pendulum, equations of motion for simple pendulum. So we have a question which says we have to obtain the equation of motion of a simple pendulum by using the Lagrangian method. That means we need to use the Lagrange equation and hence deduce the formula for its time period when the oscillations are small, for small amplitude oscillations, right? So the first step in order to obtain the equations of motion, we have to visualize what is the given system. So the given system here is that of simple pendulum. That means we have a point of suspensions. This is denoted by O, and we have some string of length L and a bob having mass m that is suspended through it. So these are the assumptions, and we have marked this angle as theta, which is the angle between the rest position of this bob and the deflected position of this bob by theta. So next step is to obtain the generalized coordinates. So for sake of simplicity, we'll use the polar coordinates over here, r and theta, because this angle is represented by theta, and whatever is the length over here of the bob from the point O, that is r. So constraint here is given to be that the length of the string that is taken to be constant, which is L. Therefore R in our case becomes L, which is fixed. Therefore constraint reduces our two generalized coordinates to one generalized coordinates, that is theta. So this is the assumptions, and this we have specified that the generalized coordinate is only depending on this theta. So now depending on this theta, we would have only one Lagrange equation, that would be del L by del theta minus d dt del L by del theta dot is equal to 0. So now note here that in Euler-Lagrange equation that we used in calculus of variation, we have t over here. T is the independent variable in all the problems that you take. The time, that is the independent variable. So this quantity remains unchanged in every time whatever problem you take. So let us now calculate this L. To determine this del L by del theta, we must know what is L. L is the difference of kinetic energy and potential energy. So the kinetic energy for the system, as is always, is given by half mv square. What is V? V is velocity, and that is the time derivative of displacement. Now you just see your bob initially was here at the point A, and it has now moved on to this direction at the point B. So what distance has it covered? The distance S has been covered. So here we would have S dot square. But you should note that the kinetic energy or whatever energy or whatever L you are calculating, the end result, this should be in the generalized coordinates, and the generalized coordinate is theta. So we have to move this S into theta. So from here, can you see, we have one angle, we have some radius, and we have this arc length as S. Therefore, we can apply this formula. The angle theta, that is equal to arc length divided by radius. The arc length over here is S, radius over here is L, and theta is as such. Therefore, S becomes L into theta. So we just replace S dot by L theta dot. L is constant, therefore its derivative is S is L theta. So taking the derivative of S, it would be taking the derivative of both these terms, right? Now this is the product, or I should write it like this. This is the derivative with respect to t of S, and what is S? It is L into theta. L being constant comes out, so it would be only be theta dot. So this is the term, and this is the kinetic energy. Now moving on to potential energy. To calculate potential energy, we can either go by considering the potential energy to be mgh, where h is the corresponding height taken from some reference point, or you can calculate the amount of work done, the amount of work that has been done on the system. So here we can take a reference point as this point A, that means at length L below the point of suspension. Now from this reference point, now our bob is at the position B. Therefore, what length has been covered from the reference point? This much length has been covered from the reference point. So H here is this one. And how to calculate this CA? So CA, this would be equal to OA minus OC. What is OA? It is the total length of the string, that is equal to L. And what is OC? Now to calculate OC, you can see here we have angle 90 degree, and because this is theta, so this angle is also theta, assuming this arc length to be a straight line. So this OC can be calculated by cos theta. What would be cos theta? It would be base upon hypotenuse. So it would be I'm sorry, here we have to take this triangle OCB. Therefore, in this triangle, this angle is theta. Therefore, cos theta would be OC divided by OB. And what is OB? It is equal to L. Therefore, our OC is equal to L into cos theta. So, this OC is L into cos theta. Therefore, this height CA, this is equal to L minus L into cos of theta. Therefore, we have just substituted this value over here, and we obtained the potential energy as mgl. We can take L common, 1 minus cos of theta. Therefore, what is L? L is evaluated by computing T minus V, kinetic energy, that is equal to half ml square theta dot square minus of V. And what is V? mgl 1 minus cos theta. So now this is L. We can evaluate del L by del theta. Now taking the partial derivative of this L with respect to theta, this term would be 0, and this term, second term, would be 0 again, and the last term would give us minus mgl sine of theta. And similarly, when we calculate del L by del theta dot, we'll take all the terms containing theta as constant, and we'll only consider the terms which contain theta dot. Therefore, the first term would be half m L square, these being constant as such. Then the derivative of this term, it would be 2 theta dot. So this 2 and 2 cancels. Therefore, we have m L square theta dot. And this term, as it does not contain theta dot, is equivalent to 0. Therefore, as we have these two terms, we can use these in the Lagrange equation. So substituting the values, now here m L square, that is constant, we can take it out, and then we can differentiate with respect to time theta dot. It would be theta double dot. So now we can take now because m and L, they are non-zero, so we can write it as g sine theta plus L double dot is equal to 0. Therefore, this becomes our equation of motion. Moreover, in the question they have been asking, what is the time period of this pendulum when the oscillations are small? When the oscillations are small, that means our angle theta, that is really small. So when our oscillation is small, theta is small, so sine theta becomes nearly equal to theta. So in that case, our equation of motion, this becomes theta double dot as such, g by L as such, sine theta reduces to theta is equal to 0. So this becomes our equation of motion, and for simple harmonic motion, we know this was our equation. Therefore, what is omega? The angular frequency that is given by square root of this quantity. So this is our angular frequency. And what is time period? Time period is given by 1, the reciprocal of the frequency, and this frequency is 2 pi nu. This is equivalent to the angular frequency. Therefore, we got the time period substituting the value of omega from here. So we have the time period as this. So you saw in this example, for calculating the equations of motion for simple pendulum, we have to create we have to visualize what is happening over here. We have to make some assumptions. We have to select the generalized coordinates and constraints, and then we can march forward to calculate kinetic energy and potential energy, and then the Lagrangian. Once you have the Lagrangian, then that is really simple to put the value of Lagrangian in the Lagrange equations and evaluate the equation of motion. So the physics behind every system should be correct to obtain the correct solutions. Well, that is it for this video. Thank you for watching.